Well, welcome everybody to the March meeting of Solar Washington. We have an exciting night for all you solar geeks, all of us solar geeks. Shouldn't call anyone out. We're going to be talking about inverters tonight. We're going to probably be getting into some good details, so put on your learning hats. Before we hear from Brian of Outback and Robin of MidNite and Tim at Blue Frog, Jeremy Smithson is going to give us a quick update on behalf of Solar Installers of Washington. And I just have a real quick update for everybody on the Solar Washington side. And then afterward, as usual, we can all head over to the Finney Market Pub and Eatery just up the street. So congrats to our newly elected Solar Washington leaders. Kendall Bodden is treasurer again this year. I'll be your president again. And welcome Dean Van Vliet to the board as our secretary, Dean. And then Wendy Wenrick, not going to get her name wrong this time. She is our new meeting coordinator. And of course, we still got Patrick as our administrative director, keeping everything together. There's the address of where we're going. And as always, thank you to all of our supporters. We are a nonprofit. We don't bring in a whole lot of money, but thanks to our sponsors and our members as well, but especially our sponsors for supporting us. Puget Sound Solar, thank you guys so much for re-upping on your gigawatt sponsorship. And without further ado, we will get to Jeremy here from SIW.
Thanks, Dave. Always try to amuse, you know. So the session's not over, but it's over for us pretty much. And yeah, those are two of our favorite legislators there. Well, it's just our favorites, you know. Jeff Morris on the right and Kevin Ranker on the left, representative and senator. Let's see if I get the buttons right on this thing. So just in case you don't know, a little background on our work with Olympia. In 2005, the Washington legislature created a solar incentive program with a limited but useful amount of funding. The intent of the program was to encourage the growth of clean energy manufacturing and clean energy construction jobs in a sustainable manner. And there was, you know, 2005 was, it was pretty slow until that bill passed, and then things started to take off. So this has really been important for our industry here. Since then, the industry has grown and created many jobs that are dependent on the program. And in 2009, the program was extended and actually created even more dependence because then in 2010 we had the in-state products beginning to appear with a much higher incentive. But the funding has not increased. As you notice, that beer bottle is still the same size. Well, lately, our friends in the various environmental groups have been advocating strongly for the increased use of solar to replace the burning of fossil fuels to make electricity, basically. And we love that idea. This is what we do. However, the current program funding is far too small to support the kind of increases that are being bandied about. And so the two I'm showing here is the governor's climate legislative and executive work group came up with a fabulous figure, I thought, 375 megawatts supported by a feed-in tariff. And Environment Washington talking about 150,000 solar roofs, which we kind of calculated out to be about 700 megawatts. But as you can see, the funding required with the in-state products is far more than what we have. And at the current market growth rate, the incentive fund could be maxed out in a couple of 3 years without the additional growth that would occur if incentive accrued to leased systems, which has been a big push of the environmental groups. If leasing is allowed in, then we've got to do something to increase the incentive fund or something. Something's got to happen, otherwise the program's going to go bust. I put together this Sankey chart that shows the money flows for a typical customer, and money and equipment, or I would just say value, the flow of value. It took me a couple minutes to explain this, but this will all be on the website. You can go take a look at it later. But here in the center, you've got your customer generator, and on the left, you've got value that accrues to that customer generator. So there's financing that comes in to pay for the system. You know, they get a loan. There's net metering, the federal tax credit, production incentive, it's a pretty fat line there because this is a Washington-made system. And then the value of the system, which is actually quite big because for this chart, I'm only looking at 6 years. And mainly, and then there's another 20 years of net metering left. So in that first 6 years, the customer pays for the loan in 5 years, gets the production incentive for 6, and 20 more years of net metering. So on the outflow, there's what they paid for the system, which is local labor to install and Washington manufacturing and equipment. They're paying back the loan. That little thin red line there is the interest on the loan. And the rest of all of that value goes to the local economy somehow. Either they just leave it in the bank or they spend it on things around them, or hopefully they don't go online and buy stuff on Amazon. But I mean, whatever they want to do with it. Anyway, you can see this is the way it is now. If we do introduce third-party ownership into the incentive program, this is what it looks like. Quite different. So you have the same flows coming in, but the only one that goes to the customer generator now is net metering. And that's really fat because I'm actually looking at 20 years now. This is a 20-year lease. And these are hypothetical figures, but they're within the realm of reality. I tried to pick some numbers that made sense. So this customer pays a lease of $84 a month instead of a $98 electric bill for 20 years. But they don't own anything at the end. So these are the lease payments here, and all these other goodies accrue to the third-party owner. And it really is this little tiny stream of value to the local economy. What comes out of the third-party owner situation is the tax equity partner gets this, the equipment and labor to install the system goes to somebody, and then there's profit. So that's kind of the way the third-party ownership picture looks. So Solar City, the Alliance for Solar Choice and Renewable Northwest Project have stepped in to try to make the program funds available to third-party owners. There are several problems with this, but the ones that we found most troublesome, Solar City claims repeatedly, I've got evidence on, you can go on TVW and see them saying these things in hearings. They claim that customers don't have full service solar companies up here that will provide financing, permitting, interconnection, monitoring, and maintenance. This is patently false, but these are their talking points that they continue to repeat. The Alliance for Solar Choice, which is a group of third-party owners, Solar City, Sunrun, Vivint, Sungevity, they claim that our utilities are attacking the solar programs in the state, which they are not. None of these organizations have acknowledged that the program will become oversubscribed and collapse if third-party owners are allowed to access the fund as things currently are. And the original intent of the program was to create local jobs and manufacturing, and that will be unfulfilled if the general fund is allowed to be siphoned off to out-of-state investors who use out-of-state labor and equipment. And why do I say that? Solar City has already installed over 100 projects here and have yet to open an office or even have a truck Everything comes out of their Portland operation. So nevertheless, solar installers of Washington would like to work with all the stakeholders to replace the existing program with one that doesn't lose its attractiveness in the last 3 years, as ours currently does, and I won't go into an explanation of that. But in this legislative session, that meant working with our friend Jeff Morris, who's the chairman of the House Technology Committee, because he revived House Bill 1301 from the previous session and introduced House Bill 2176, and a placeholder bill, Senate Bill 6541, was created in the Senate in the event that Representative Morris's bills did move through the House. Then we'd have something, a framework to hang another bill on in the Senate and try to get something together between both houses. The resulting floor amendments of Representative Morris's bills needed work, a lot of work, but we had hoped to move them to the Senate for further revision. That was kind of our strategy. The process was messy, with a cast of characters that couldn't seem to come to an agreement on what should be done, and so both of those bills died in basically in the Rules Committee, waiting to be enacted on the floor of the House. So where do we go from here? Well, we find ourselves on the horns of a dilemma with an incentive program that has nurtured a market for manufacturers and installers up to this point, but that will actually stifle the overall market going ahead. And the pointy parts of those horns are at 54 cents a kilowatt hour. The incentive funding cap could be reached in a couple of years at our current growth rate. At 15 cents a kilowatt hour, which is the out-of-state rate, that fund can be stretched farther, but in-state manufacturing would collapse. Leasing of solar to customers has advantages. People that can't use the tax credit, for instance, retired people, self-employed people, what have you. And disadvantages, just as ownership of these systems has advantages and disadvantages. A mixture of the two in an incentive program could work, but companies with 20-year leases would tend to dominate the market because it's a real easy sell. You just say, hey, you want to pay less electricity, you have solar in your house, sign here, done. Utilities are concerned about so-called cost shifting, even though it isn't really a problem for them yet. They're looking in the future and figuring that it could be a problem. The additional incentive funding may not be politically feasible for several years. So we've talked to the legislators about getting more money for the incentive program, and because of the decision on education that is going to cost another $2 billion and various other things, we're kind of at the end of the line. Maybe looking at 2018, we heard. That's what I heard anyway from Dave Warren of the PUD Association. Environmental organizations, although they are Johnny-come-lately to solar, I hate to say it, you guys, but you used to tell us no solar, too expensive. Now they just want to carpet the state with solar. Installing companies are facing an uncertain future of incentives, but we're expected to grow. So these are some difficult issues to deal with, but that's why we're here, Solar Installers of Washington. So over the next months, we'll be wrestling with all these things, and we will keep you up to date. Thanks very much. Any questions? Oh. Oh, okay, wait a minute. I'm going to get you a mic. And we see your questions there online, so hang on a sec.
Yeah, I was wondering if anybody has started putting together numbers of how much better off the state is because of all the installers and the manufacturers and the service people that have been paying taxes since 2005.
That's a good question. It's tough to get your hand on those numbers. We did present some numbers to in a committee hearing in the Senate, and it's been estimated there's about 1,300 jobs that's been created in the state of Washington so far. That's done by a national organization. We did our own kind of guesstimates based on the volume of business that all of the solar installers have done, projecting how much in B&O taxes have been paid and kind of how much sales tax trickles out from that, that income stream through employees, et cetera. And it's significant. The leverage, actually, of the state money is really good. It actually comes back to the state quite nicely. Yeah, it's a good argument to make. Hopefully, we'll be able to hone in on some of those numbers. But yeah, the question that we get, in fact, when we did the solar installers on the Hill thing back in January, the feedback that we got from one of the legislators' aides was, give us those numbers. If you have real numbers, and our lobbyist Brad Boswell has been encouraging us to do that too, because there's a lot of talk on the Hill, but when you have actual facts and figures, it's a big deal. So online, we have a question here. Well, that's a good question. If we continue with the growth rate that we've had at 54 cents a kilowatt hour, it could be 2 or 3 years before we hit the. Now, this is in general. The reality is that the funding cap goes by utility district, but where all the solar is being installed, we definitely could be hitting those caps. In some places, they've already, like Jefferson, yeah, Jefferson PUD. But in general, yeah. And what is the cap? It's about 23 million, 22 something. Yeah. Okay. Any other questions? So as the law is currently written, then everybody's incentive gets prorated according to how much money there is. So basically, it begins to get watered down, which is not so bad for the people that are in the program now, but it makes it difficult going forward. But it means you still do have a program. It doesn't just like suddenly end. Pam, you had it.
And I just wanted to say that I recently went through the Solar City evaluation on my son's home in Los Angeles, wanting to take a look at the difference between buying and leasing. And one of the things that had me right away was when I realized a lot of the environmental groups are saying, well, this is the way poor people can do this, Well, the reality is the first thing they ask you is, what is your credit score? And you still have to have that, I think it's 600 credit score to participate in Solar City. So it's not like this is going to be a magic bullet for people that couldn't afford to get a loan. So again, I think the loan program is something that we just need to encourage people. They haven't had a chance to take a look at it, to run the numbers with Puget Sound Cooperative Credit Union. They could do that, and it would be it might be a something that they didn't expect to be able to do.
Any other questions? Okay, so I guess we'll move along here. All right, thanks.
All right, so next up is Brian Faley from Outback Power, and we have about a half hour each for the next 3 speakers. If you want to go for about 20, I'll give you a warning at 20. I'll give you 5 minutes, and then we can take 5 minutes of questions and answers.
Great. Good evening. I'm Brian Faley from Outback Power. I've been in inverters for 32 years, and I'm going to cover 32 years of progress in 20 minutes. Okay. In the beginning, technology was pretty primitive in the beginning, and the bottom of that picture there is a schematic of the entire guts of the logic board for an early inverter in 1980s technology. It's pretty small and it's all discrete logic, and it fits on about a 4x4 card. The size of the cards today hasn't changed a whole lot. The functionality's changed dramatically. And on the right there is a power semiconductor device that you remove with a wrench. So it was serious stuff back then, very slow devices. Just to put it into perspective, compared to today's semiconductors, it's about the new ones today switch about 1,000 times faster than that one did. But the cost is about the same. Washington inverter technology goes back quite a long way. 1976, company formed in Ballard. In fact, my first employer as an inverter designer, engineer, was Dynamote Corporation, which is about less than 5 miles from here. So this is kind of where I grew up, this area. This is my stomping grounds. It's kind of fun to come back. In the early 80s, this is before power MOSFETs were around. Power MOSFETs are kind of the semiconductor device that made power inverters useful and low cost and powerful. But this is long before that, and we built a line of inverters. We covered the span of 500 watts to 6 kilowatts. We used devices called SCRs, which are old and slow, and they have memories like elephants. So you can turn them on, but you can't turn them off directly, which meant you had to use something else to turn them off, and then you had to use something to turn the other thing off. So it was quite a lot of work to get it to work. On our high voltage inverters, it ran on 120 volts DC, which was a string of 100 amp hour golf cart batteries. We had pretty high efficiencies. It's in the 90 and 94% range, but the output voltage is not a sine wave or anything like it. It's a square wave, and it really was square, which means the total harmonic distortion is right around 45%, which means that motors don't like it very much. Light bulbs didn't mind it, but they sung. The idle power was a whopping 1 amp. Idle current was an amp on a 120 volt inverter. That's 120 watts. So solar panels of the day were roughly 30 to 40 watts. So you think of the amount of energy you're wasting every day. It was pretty amazing that anybody even used it, but people did. Didn't have any voltage regulation, and it was really heavy. The small 6,000 watt inverter weighed about 120 pounds. So the first industry response was voltage regulation, because that was a real issue, particularly when you had sensitive loads. You wanted to run anything other than just light bulbs, or we did run well pumps, so they didn't like it a whole lot, but you could run them. So the first MOSFET-based inverters, when the MOSFET became available in the late 80s, provided voltage regulation, and the way it did it was to modulate the waveform, the amount of time you spent on. And so that if you look in the lower corner, any of you who've read articles in Home Power or anything like that, you've seen the modified quote-unquote sine wave waveform, which is the red waveform next to the green sine wave, which is what your desirable waveform is. And I'm showing what became the de facto topology of the day, which was an H-bridge inverter, which drove the primary of a transformer. The original inverter started out with what was called a push-pull circuit, and they gradually migrated to the H-bridge because the H-bridge provided some waveform advantages. That was kind of pioneered by companies like Trace, and actually Dynamote had some product that did it, and some out-of-state inverters as well. But this is an example. You probably use, if anybody's been around a while, you'll Trace U-series. It was a great, inverter. The waveform is on the lower right, and you can see that it's definitely not a sine wave, but it approximates a sine wave for a lot of loads. One of the things that crept up during that same time period was regulatory agencies began to take a look at inverters and decided that they really wanted to regulate them, the manufacture of them, the safety of them, and UL got in the ball game and pushed for inverter standards. Trace was one of the first companies that actually adhered to the standards and listed the product. And I'm only mentioning that because in order to do that, you spend a lot of money and you spend a lot of time, and it doesn't add a lot of value to the product, but what it adds is customer confidence. This is kind of a funky chart. This is actually a series of waveforms overlaid on top of each other versus battery voltage. And so one of the difficulties with the quasi-square wave inverters or quasi-sine wave inverters, depending on how you wanted to call them, was that the simple voltage regulation method, the only thing it had to do was it could adjust the amount of time that it spent on. And so as the voltage rate would go up, the amount of time it was spent on would drop, and as the voltage lowered, the amount of time it spent on was greater. So as you reached low battery, the output was almost a pure square wave, and as you reached high battery, the voltage could go up as high as 190 volts, which devices didn't like a whole lot. The other problem, well, that we kind of solved was any systems you ran off of this, particularly audio systems, televisions, they didn't particularly care for the waveform either, and they responded by either giving you something like hum in the audio, which is kind of annoying, and also if you had a television set, you had an annoying roll of the horizontal bar because it wouldn't lock the waveform synchronization. Those were solved by changing the frequency of the inverters slightly so that they didn't roll anymore, but you still had the lines, and it was still annoying. And then along came the sine wave. Sine waves are really alluring. It was alluring to make them, and it was quite tricky to do. Basically, every manufacturer that I know of worked on sine waves in the lab. There were, by the mid to early 90s, there were 3 inverter companies in Washington. There was Dynamo, there was Hart Interface in Kent, there was Trace Engineering, which is a bunch of guys who left Hart, formed up in Arlington. And they were all, I think all of us at one point were working on sine waves in our labs, and we had some demonstration products that came out. As early as 1984, we came out with a sine wave inverter. We actually debuted it at a big renewable energy show in Anaheim, California, called RETSI. It was a 3,600 watt inverter. It weighed 26 pounds, so it was really small and lightweight. It had quite a nice waveform, and it proved impossible to produce. The following year, I think it was 2 years later, we were still showing the same inverter. We're trying to produce it. We made a few of them, like 15, so we can say we actually built them. Hart came out with a sine wave inverter, kind of a we can do it too, which also was never commercially reproduced in quantity because they decided they weren't going to pay the contractor who designed it for them. Not very nice. So neither were really produced in commercial quantities. In about 88 thereabouts, the company I was with, Dynamo, came out with what we call the Brutus, and the Brutus is this beast on the lower left there. It was the first commercially available sine wave inverter that used an H-bridge topology. It was 2.3 to 2.4 kilowatts at 12 volts. It was a beast. Richard Perez of Home Power Magazine actually did a review of it and said he threw everything he possibly could at it. He couldn't break it, and it would still keep running. So it was quite a deal. The downside of it was the idle current was right around 7 amps, and that's a lot of power, 96 watts or so. So Trace, which was going guns up in Arlington by that time, responded with the SW inverter, and I call it the Swiss Army knife inverter because it basically was so powerful and programmable you could do just about anything you wanted with it, which is great if you like to diddle with things. It was also the first grid-tied battery-based inverter, and I'm going to refer to battery-based inverters over and over again because that's kind of what's differentiated the Washington inverters from most of the other inverters you might be familiar with, particularly in the PV world. And one of the advantages, of course, of the battery-based inverters, you've got local energy storage. And in the climate where you only have 4.3 kilowatt hours of sun per day, that could be a big deal when you want to have the light shining 24 hours a day. The difference in the technology between these was the Trace unit used 3 transformers to synthesize a waveform from lower frequency, from 3 lower frequency waveforms. And the waveform is a stepped sine wave, and you can see the stepped sine wave over on the right, and it really does look like that. The advantage to it was that it had a low idle current. You had a low amount of idle power. So it was one of the first useful and very usable sine wave inverters on the market. and it really brought the sine wave to mainstream. Before this, they were used in places where they had critical loads and where you could put up with the extra idle current. But in most systems, you needed another 2 panels just to run the stupid inverter. And some, well, let's see, is that the next one? Yep, it is. Well, of course, you all have heard the stories of the demise of Trace. Stat Power was a company in Canada that built small, lightweight, high-frequency inverters. We called them toy inverters. They acquired a power supply company called Xantrex, and Xantrex got on a power-hungry trip to buy up everything they could buy. They merged with Trace, and then they bought Hard Interface and Cruising Equipment, and then half or more than half of the inverter designers left or were fired, or some of both. Outback was formed by former Trace employees, went after the off-grid and the grid-tied markets. Magnum Energy, which is a company that I'm formerly with as well, was also formed by Trace employees who went after the off-grid and mobile markets. A few years later, Schneider bought Xantrex, and then a few years later than that, Alpha Technologies bought Outback, and there's rumors that there's more mergers and acquisitions in the woods. As far as innovations, Washington inverter companies have actually made some pretty major innovations. One of them was battery-based inverters with and without grid-tie capabilities. They're bidirectional inverters. They can charge your batteries from the AC. They can convert from DC to AC like normal. Most of them use a simple topology, which is a single conversion topology, which is very high efficiency, because every time you convert energy, you take a hit in terms of efficiency. So if you have a double stage inverter and each stage is 90% efficient, your overall efficiency is only 81 because you get the product of the two. So to make a really highly efficient high frequency inverter with double conversion is very tricky, and it takes a lot of money because you got to have so many semiconductors in it. The other thing that Outback started was the idea of a sealed inverter that was environmentally sealed from the elements, and you could take it anywhere. Rugged construction became another piece of that. All those products were built around that. And reliable operation, because we really didn't want to staff technical phone lines with lots of people to complain with people dealing with broken inverter complaints. We wanted to build inverters that worked and stayed working. And the other part of that was field replaceable components. There's a lot of inverter manufacturers who want you to return it when it's broken. Some of the other technical innovations were clip mounting. Let's see, somewhere in this thing. Yeah, you can see the clips in this one. This hold the transistors in place. Surface mounting of power MOSFETs that's a Magnum product over there. Some of the other things, single axis assembly to make it faster to produce, replaceable power boards, field upgradable firmware. Think about that, relatively nice thing, but it's also kind of complicated as well. The ability for inverters to data log, having parameters that can be programmable, which makes them flexible, paralleling for higher powers, so you can scale them up in bigger units or larger systems, and finally UL compliance. And the UL spec that you get into with grid tie inverters is 1741, and it's getting more and more complicated. Some of the current challenges, I would say a lot of them are regulatory requirements, and that's driving the technology we use to apply in inverters. They're becoming more stringent. EMI requirements, FCC Class B, so you don't pollute the radio waves around you. UL 1741 is going through some major rewrites right now with the smart grid parameters being added. DC arc fault, which has been a huge issue in large-scale inverter systems, is migrating down into smaller systems. And we have to maintain compliance with that. Anti-C code changes as well that kind of accompany that. As soon as you move to higher voltages and string inverters or large strings of panels, you have the possibility of arc fault. That's something that has to be addressed. And then the utility environment itself is becoming increasingly challenging, particularly as in areas where there's high PV penetration that's grid connected, because it destabilizes the grid. And no matter how you want to think otherwise about it, the reality is in those areas where there is large numbers of inverters, Hawaii is a good example, there's areas of California as well, they destabilize the grid. And so there's changes in the rulings and the rules and the way that we operate that are being implemented to try to restabilize things. It makes the inverter design more complicated, but it makes the grid more stable. Along those lines, things like smart grid, which is a series of rules or ways of operating so we can all get along in a system that was never set up for distributed resources. I mean, if you think of a normal system operator in a utility has a couple of points of generation and lots of points of load. As soon as you spread out multiple points of generation that aren't under their control, under their umbrella, they can't handle, they can't make changes to the grid to respond to changes that are going on in local levels where power is being pushed back into the grid at larger levels than it's being consumed. That's something that smart grid can address. And SunSpec, which I put on here, it's just an alliance of inverter companies working together to come up with a common standard for interaction, particularly around the smart grid. So in terms of where the technology is moving, it's in the area of complex control and intelligence. We're having to make these inverters. They went from the first schematic I showed you, which was a bone stupid inverter that all it knew how to do was make square waves, to inverters now they're supposed to know when they shift the frequency around, when they respond to operating conditions locally that they're being provided with, or they take commands from systems far away. That requires more levels of complexity. And the communications between inverters, that's becoming more and more complicated because we're passing more information, because people want more sophisticated systems that they can monitor and control from a distance. You want to pull it up on your iPad or your iPhone and check on system status. If you're an installer, you want to be able to check on your installed base of products and make sure they're functioning. All those things are significant, and they're sort of beyond the idea of just simple power conversion. It gets into energy management. These are just a couple slides on the smart grid and what it means. The specifications right now are, there's been a proposal in the smart grid inverter working group to change 1741, which is revolves around the utility compliance of the inverters and what range of voltage and frequency it can operate over and still maintain a connection to the grid. And the first category is called the autonomous function. And what the autonomous function means, this is a set of parameters the inverters comes factory programmed from. It doesn't require any outside input from the utility company at all to activate it. It'll activate under certain conditions in different ways. So the autonomous functions are basically things we're building in to allow ride-through of faults. Right now, as soon as the grid falls out of voltage spec, we're required to disconnect, and then we're required to reconnect when it comes back into compliance. Well, if you have a huge number of inverters connected to the grid and they all drop out all at once, that's a very destabilizing event. Similarly, when the inverters think that they can come on again 5 minutes later, when they all come on in a big group, that's also destabilizing to the grid. So one of the things the first level the smart grid function does is allows the inverters to ride through voltage dips and sags and small frequency shifts that happen over a short period of time, so it doesn't all come offline immediately. It allows them to back off gracefully, and when they come back on, they can come back on in a staggered fashion. All those things required significant rewriting of the code, and that right now is getting close to a vote. So there's 3 phases to the smart grid initiative, and one of them is the autonomous functions, which I mentioned. Then there's a phase 2 and a phase 3. And the phase 2 is communications technology. So we're adding into the ability to expand the parameters. We're adding in the ability for it to be addressed by a utility company. In order to do that, a lot of this work is simply around security and transport protocols. What's the data that we're pushing back and forth, how it's being transmitted, what the method of getting it there is, what the infrastructure required to get it there. It's just a lot of work. We're trying to be, responsive to this stuff. It's a massive requirement on the inverter in terms of the software function. I mean, this isn't something the inverter designer is working on. This got a whole raft of software engineers trying to figure this stuff out. And then as we get into phase 3, there's additional ones particularly revolved around not just monitoring information, but also controlling things. They'll be able to turn you off if you're overproducing in an area. They'll be able to connect you and disconnect you, limit the amount of power you can produce during certain times of the day. DER is distributed energy resource. They get into all these acronyms and buzzwords. Thanks for asking that. There's some regions that we need to keep tabs on because they kind of are leading in terms of where the industry and the technology is going. Unfortunately, some of them are leading in ways we don't like a whole lot. As soon as you get utilities trying to limit the connection of PV or solar, we kind of get antsy about that because it affects our markets. There's areas of California right now we're not able to sell inverters into because they don't have connect agreements, and they're based on the idea that if you have a battery-based inverter connected to the utility grid, if someone was clever, they could buy power when it was cheap and they could sell power back when it was expensive by just gaming the utility and sucking energy into your battery and then discharging it. What they're not looking at is the cost of the battery. You're wearing your battery out for something you're not getting paid a whole lot of money for. It doesn't make sense on that standpoint, but it's requiring changes in the way we make inverters operate. So places like the European markets where they have high levels of penetration, they're changing the feed-in tariffs. In Hawaii, you've got high solar penetration, destabilizing the grid there. And they've responded by saying, look, we can't afford to destabilize the grids. You guys have got to make changes to the way you do things. And we're saying, well, you got to tell us what we need to do, and you've got to pay people if you're going to take their resources offline. Another thing we're seeing is we're seeing sizes of systems going up because PV costs are coming down. So the average size of a PV system is moving significantly larger. Where we see that in terms of the inverters we sell a lot of inverters now into AC coupling applications where people want, it gets back to the battery roots, they want energy storage in systems that don't have energy storage. And so one of our advantages of making battery-based inverters is that we can sell systems to support other inverters with a backup capability. Some battery storage technologies. Obviously, the future is in the advanced batteries. Those require a high degree of maintenance and interaction, so much more sophisticated communication. So if you look at the resources that an inverter manufacturer has to devote to these things, there's a lot less energy devoted to the actual art of power conversion. That's like you have to do that. But in addition to that, you got all the other crap you got to do, like make sure it can connect to the rest of the world. That can be controlled, and then it's future-proof so that in 2 years when the utilities change their mind about something, you're not stuck there saying, well, dang, my inverter can't do that. And that gets to the communications. Obviously, people want to be able to communicate through things with their smart devices, and that means you got to have Wi-Fi, or you got to have Bluetooth, you got to have something else that you wouldn't have dreamed of 10 years ago. Whoever thought an inverter would need Wi-Fi? Is it going to stream Netflix next? Well, stay tuned. Okay, so in terms of the technology trends, where things are headed in the inverter industry, DSP, or digital signal processing technology, is used extensively now in inverters. It didn't used to be, but it has to be in order to give us the control over how things operate. Part of that is that cost of those components has come down dramatically in the last couple of years, and the power has increased significantly. That reduces our time to market and allows us to get important functions into products quickly. The power semiconductor technology is running into some game-changing new technologies that are going to come out in the next few years, and we're definitely on top of that. With the high power and high power systems, the integrating form factors, increased system sizes, we have to make these inverters bigger, smaller, lighter, more cost effective. And then energy storage, integrated energy storage as part of the system becomes more and more of a critical piece, particularly as you get into sophisticated chemistries like lithium-ion, where you have to actively manage the battery during all of its charging and discharging. It's a lot more complicated than it is just stick a lead-acid battery on it and don't worry about overcharging because it'll just bubble a little bit. Lithiums catch on fire. Communications, it's all about that. Real-time communications, performance data, inverter parameters. And that's crucial to system management, both on your own system, but also as larger systems are formed with grids and microgrids. So that's 32 years in 20 minutes. Any questions?
Brian, one of the things that has come up as electric cars proliferate is the use of high voltage battery packs from cars to run inverters. Is Outback looking at any of those kind of things? Because then you're constrained to whatever the voltage is coming out of that battery pack.
To say that yes, I would say yes, we are definitely looking. We're looking at all forms of energy storage. We have alliances with a number of battery companies. We sell a battery that we have produced for us already. We've been very active in that and trying to understand how that would work, particularly when you get into warranties on vehicles. You know, what happens when I'm using my battery, cycling my battery at night, that kind of stuff. So yeah, we're definitely looking at the ability to use other storage, existing storage mechanisms. Obviously, that changes the technology a bit, but that's a direction we're definitely taking a look in. Anybody else?
Hey, so is Outback involved in or taking part in the UPS projects that are going on in the military to reduce generator runtime at bases? I've been following, basically adding batteries with inverters to generator systems.
We have in the past, and we continue to have projects. There's a lot of stuff going on to reduce generator runtime, and we have inverters to support those functions. So yeah, definitely. Not just military, but all kinds of different applications. Certainly off-grid for one.
So to piggyback on Jeremy's presentation, in what ways is the production incentive for Washington State inverters, in what ways does that affect Outback's business, either now or maybe future plans?
That's a really good question. I've been with Outback since December, so I really can say I don't know. We definitely sell systems into Washington State, but I would say as the largest percentage of our customers, they're not in Washington State. So that will have some impact. I just can't tell you what. Definitely we want to support it. I mean, we build grid connectable inverters. So, but in terms of what the impact would be on that, I really couldn't tell you. The majority of the systems being installed are batteryless inverters right now in Washington. So if people want battery backup, they'll install our systems, or they'll install an AC coupled system. Anything else? Thank you very much.
All right. And Robin Gudgel from MidNite Solar, you are up. Did I get your name right? I want to get it right. Robin Gudgel. Thank you.
I'd like to pass this around. This is a sample casting that was actually part of the Rudolph test where we ran over with our partner 3 or 4 times. So you'll see some scratches on the back. And look at the very back of it. You'll see some very strange writing. If I remember, I'm going to ask if anybody here understands what that writing is at the end of this. My talk's going to be a lot different than Brian's. Brian was very technical. Can you hear me? Mine's going to be more product-based, but just to give you an idea of my background, I've been doing this for about 25 years. Brian did talk a little bit about communications, cell phones. This is something that we just released. This is one of our charge controllers that you can now view on your cell phone. Two-way communications. Very interesting. I don't know how many of you know my background, but I worked at this company called Trace Engineering that you saw. In fact, I was the mechanical engineer on all of those Trace Engineering inverters. I was there for 10 years. When Xantrex bought Trace Engineering, I was one of the owners of Trace, and therefore I was one of the owners of Xantrex when they bought Trace. And that lasted for a couple of years until they had the foresight to fire me. The next day I started this company called Outback Power Systems. I was the founder and president there for 5 years until that wasn't any fun anymore, and then I started MidNite Solar. And I've done an awful lot of design work for Magnum Energy as well. In fact, my wife's son is one of the founders and owners of Magnum. Unless they were sold last week, I'm not quite sure. That's the rumor that we don't know anything about, right, Brian? Yeah, Brian and I worked at Trace Engineering. Bobby, my brother, he was at Trace and Outback and Magnum, MidNite. This is a very incestuous industry up here in the Pacific Northwest, by the way. Well, yeah. So we're going to talk, since most of you are going to be grid tie installers and probably haven't done a lot of battery-based stuff, I was going to go over some of the MidNite products, starting with charge controllers, and I'll work up to inverters towards the end. But it's just an overview of our products, actually. Brian covered the industry of inverters quite well. And if you want to see more on our website, midnitesolar.com, there is a history of the Northwest inverter companies. Where it actually all started before Trace Engineering is there was 4 or 5 or 6 of us that used to be in the hi-fi business. Some of you old-timers might remember a company called Phase Linear. Bob Carver from Carver Corporation. That's where Bob and I and the original owners of Trace Engineering all learned about power electronics. And we went from there to design inverters. Let's see if I can figure out how to work this. Charge controllers. By the way, it's hard to do anything in a half an hour. So I'm going to go through some of this very quick. If you've got questions, just holler out. It's easier for me to answer a question because that way you're actually getting information that you really want to know about rather than what I think you want to know about. This is just a new charge controller. This is the casting that's floating around here right now. All of our products, by the way, unlike the other Washington-made companies, other than the solar panels, iTech and Silicon Energy are actually made in Washington State. All the, pardon me? That's right. Magnum actually builds all of their circuit boards and their products in Washington State, and hopefully it'll continue that way. MidNite Solar, we do all of our own circuit board assembly right in-house. We build all of our products right in Arlington, Washington, just a few blocks from where Trace Engineering started. And we're a few blocks away from Outback. Although Outback manufactures most of their stuff offshore, as well as, well, most of the companies that build products. We actually, this is, yeah, the charge controllers that MidNite makes are the only charge controllers, to my knowledge, that are actually made in the United States. Fully manufactured here. The Kid, which is this one going around, is a little 30-amp charge controller. It's not really designed for like grid tie or battery backed up grid tie. It's designed for smaller systems where you only need 30 amps of power, boats, RVs, or small cabins. But as your needs grow, you can actually parallel 2 of the Kids together, and now you've got a 60-amp controller, and now it's starting to get pretty powerful. Paralleling the inputs and the outputs is something that you cannot do with any other charge controller, to my knowledge. You can always string a lot of them together on the outputs being paralleled, and they do a coordinated charge. But you would typically go to a much larger controller if you're going to have, you know, more than a couple thousand watts. You can see it's very programmable. I talked about the input paralleling. So you can get a single 60-amp controller, but you don't have to start with the cost of a 60-amp controller. This is retails for $400, by the way. It's actually pretty inexpensive. So here you get an idea of how much power you can get out of the Kid. We call it the Kid because Mario, the engineer, is 22 years old, and he started working for us when he was 17, still in high school. He's a kid. He learned a lot from Bob, and this is his product. It does support 12, 24, and 48-volt battery banks. So even though it's not necessarily a renewable energy product for grid tie or battery backed up grid tie, you'll see it in lots and lots of applications because it's just a cool charge controller and it's fairly inexpensive. Whiz-Bang Jr. It's a funny name for a little product. What the Whiz-Bang Jr. does is it turns our charge controllers into a state of charge meter. So some of you may be familiar with the Outback FNDC, the Magnum BMK, the old cruising equipment meter, the E-meter, or there's lots of, I guess the most popular one out there is the Bogart Engineering Trimetrics. Well, with this little $59 board, it turns both of our charge controllers into a state of charge meter as well. That's what it looks like there. All the firmware on the kit is upgradable. We'll keep on coming out with new features probably for the next year. We haven't added wind. We haven't added a lot of lighting controllers. This is a great little lighting controller as well. But you can just upgrade the software. It's drag and drop, which is actually pretty easy to use. I can do it. I'm a mechanical engineer. I'm not an electrical geek. So it's got to be pretty easy if I can upgrade the software. The Classic. The Classic we've been producing now for a little over 3 years. And it is now actually shipping with the Whiz-Bang Jr. at no extra cost. It is by far the world's most sophisticated charge controller. We now have 13 man-years of engineering into the Classic. When Bob designed the original Outback charge controller, it took him about 1.5 years all by himself. And we have 13 years into this. So either he got really lazy or this is just very, very sophisticated. And I think I know the answer to that. These are just some of the features. I don't think we need to waste a lot of time on them right now because we only have a half an hour. But we do have 150, 200, and 250 volt inputs. Somebody's asking about like Priuses. Although I don't know that it's a great idea to drain your Prius battery to charge your, to do grid tie stuff. Some people have done it with a Classic because we do go up to 250 volts. It's right on the very edge of what you can do with the Prius battery. We don't recommend it, but the equipment can do it, certainly. But I don't know if you want to ruin your Prius battery just to charge a battery-based inverter. Solar panels are cheap these days. We also have what we call the Classic Light. Same voltages, same power. These things are good for some of them almost 5,000 watts. They have internet built in. There are a couple of charge controllers that do have internet built in, Morningstar and the MidNite. And again, the MidNite's the only charge controller that's fully built in the U.S. We also do wind. Is there any wind guys here at all? Ah, good. Wait another few months. We've been designing a wind turbine for the U.S. Army we'll be coming out with, as well as some special charge controllers, and well, we're working on grid tie inverters for that as well. Communications. Like I said, all of the Classics and Classic Lights do have Ethernet. We have RS-232, which is used for our internal language that speaks from Classic to Classic. In fact, speaking of Classic to Classic, one of the next things Bobby's working on is actually making the Classic talk. Every Classic we've ever shipped is capable of actually talking. And in the next few months, we'll be releasing that software. We're not sure what it's going to say yet, but expect a little humor there for some of the things. If you know Bobby, well, it might burp at you. I'm not quite sure. One thing a couple things we've added to the Classic is DC GFP, ground fault protectors. I think Xantrex has this, or Schneider has it built into their XW. And we also have DC arc fault. And I believe it's still the only charge controller in the world that has DC arc fault. It actually works. Now what's interesting about that is it's been a requirement since 2011. However, most of the charge controllers get installed in off-grid. And off-grid definitely gets treated differently than grid tie. A lot of the systems are not inspected, and it's not enforced. There's only a few places that are actually enforcing arc fault for charge controllers. They're certainly enforcing it for grid tie inverters now. But we've had it for 3 years, and it actually works quite well. We don't really care for ground fault protection. I don't think it stops fires. I think it can electrocute people, where the DC arc fault actually stops fires. Same thing with the Classic. It is firmware upgradable. We just put the updates right on our website. And as we come up with new features, such as speech, we just released a new software version a few weeks ago for state of charge. Again, everybody that's had a Classic for the past 3.5 years can now have state of charge. All they need to do is buy a $59 Whiz-Bang Junior. And have any of you used state of charge meters? Okay, well, yeah, Dean. Yeah. Anyway, they cost a lot more than $59. The one we have is extremely accurate. It does 0.1 amp resolution because we put the Whiz-Bang Junior, the electronics, right on the shunt, which is where they really need to be. So they don't pick up noise on your twisted wires and things like that. Works very well. Monitoring. I showed you the local app on the phone here. We also have that available on your PC, either hooked up directly to your PC, or you can be sitting on the beach in Spain, call up your computer or your system here and change any of your battery charging functions or put it in EQ mode or look at the history of what your system's been doing. The Classic does save 6 different parameters for 380 days. While it's hooked up to the local app over the internet, it is logging 11 different items. So that's what we call the local app, and you do have to do port forwarding on that one. We also have this thing called My MidNite, totally separate software, and this one is more plug and play, so guys like myself like it, since I'm not an electronics geek. Every Classic automatically calls out to My MidNite. And when it's hooked up, you can look at 3 different things on the screen. It is data logging as it's monitored or as it's hooked up. And you can pick from, I think, about 10 or 11 different things that you can look at. You can only look at 3 things at one time, though. So here's the local app again. And now you can get the state of charge right on that screen too. So you can actually get it on your cell phone from any place in the world. You can be monitoring your system. And in about 30 days, this will work on an iPhone as well. All the software is free, by the way. You buy a Classic, you've got it. Auxiliary outputs are just very useful things. I'm not going to read them all off what they do, but we have 2 auxiliary outputs. I think everyone else with charge controllers has 1. So you can be doing 2 different things. Load diversion, turning on and off lights, various different things that are just very useful to do. Okay, we talked about the Whiz-Bang Junior. It mounts directly to a shunt. I guess we're not showing a shunt here. But pretty much every system circuit breaker box I've designed for the past 25 years or so has a built-in shunt. So if you've got an Outback system, even the Magnum, any of the MidNite systems, or the old Trace systems, they all came with 500 amp 50 millivolt shunts. And that's what the Whiz-Bang Junior bolts to. So it's very standard across the entire North American inverter industry. We talked about state of charge. This one says it's 74%. Tells you how many amp hours are remaining. A lot of useful information. It's very simple to read. Something else we have that's easy to use, and it really helps to uncomplicate the fact that we have 6 different large charge controllers. You don't always know which one to use. Why would we have a 150, 200, and 250 volt unit? Well, a lot of times it's just because of the distance from the solar panels to the batteries. What this is our string sizing tool on the website. We have one for the Kid and a different one for the Classics. But what you'll do is you basically tell it what your solar system is, how many solar panels in series, how many parallel strings, and then you play the what-if game. You hit the button and it tells you which Classics are the right one to use, which is a good application. It tells you when you're going to go into HyperVOC, which I don't think I have a slide of HyperVOC. It does get a little cold here, and you guys are used to designing string sizes that don't exceed a maximum voltage, right? What happens when you exceed that magic voltage? They go up in smoke, don't they? What happens with the Classic when you exceed the operating voltage is it does not go up in smoke. It goes into what's called HyperVOC mode. And that's a non-operating mode where you get to add the battery voltage to the maximum operating voltage, and it's a safe voltage. So if you have a 48 volt battery bank and you have a 150 volt Classic, your solar panels could actually go all the way up to 200 volts and it's not going to break. Try that with our competitors. Try it lots of times. The results will be the same every single time. The Kid also has HyperVOC, by the way. So if you have a 12 volt battery, you really only get to go up to 162 volts. All bets are off beyond that. A lot of guys that do our Classic with wind, like Berge, it's the standard controller for Berge, and they use our 250. Well, they've designed the stator to never go over 250 volts. And in fact, we have never seen a voltage over 400 volts coming out of the Berge. We've only broken one, by the way. I'm impressed. So the HyperVOC works. It works very well. And the Classic is, or all the MidNite controllers are the only controllers I'm aware of that have HyperVOC. So what it's really designed for, by the way, is on cold mornings before the solar or the sun has actually hit the solar panels, that's when you're going to get the highest voltage coming into the charge controller. And as soon as the sun hits the solar panels, the voltage drops. But at that one little point early in the morning on a cold morning is when you're going to break charge controllers. So we just say, we're not going to play. We're not going to turn on. Let's go into HyperVOC mode. And now you get to add the battery voltage to that magic 150 or 200 or 250 volts. So you can basically go up to 300 volts on our Classic 250 with a 48 volt battery bank, and it's not going to hurt it. It just won't work until the voltage drops down to 250 volts. Anyway, the string sizing tool is very, very useful for figuring out which charge controller you really want to use. Oh, here's HyperVOC. So this shows you how it works. You'll see the PV voltage ramping up early in the morning, and it hits that 150 volts, and then it turns purple. It continues to climb until it reaches that magic number of 175 volts or so. And it stays there for a while until the sun actually hit the solar panels. Then the voltage starts dropping, and it gets to the 150 volts again, and it tries to turn on. There's not enough power originally for it to turn on, so it has to try a few times. Once it's got enough power to overcome the idle losses, it just turns on, drags the solar panels down even further, and it produces power for the rest of the day. So that's how HyperVOC works. Follow me mode is something that's very important. It only takes a telephone wire to connect up. We don't need hubs or special routers or anything like that. These solar systems have gotten so large lately that one controller quite often is not large enough. And if you don't have a coordinated charge on, let's say you had 3 or 4 charge controllers because you got a big array. What's going to happen if they're not a coordinated charge is you're going to destroy your batteries, because one charge controller will go to float, and then another one goes to float, and then a third one goes to float. And those 3 charge controllers that went to float are no longer putting any power into the batteries. It's that 4th controller that is now trying to satisfy the requirements to go to float, and it doesn't have enough power to do it because you've obviously got a large battery bank if you've got 4 charge controllers. So what happens is it can stay in a bulk charge all day long, every single day, and that will destroy your batteries. So we have this mode called Follow Me, and like I said, it doesn't require a hub or anything like that. It's just that the first charge controller that decides it's time to go to float, it sends a signal to the one next to it. It says, hey, I want to float, follow me. And then that one goes to float, and it sends a signal down the line to the next guy, and it goes all the way back to the beginning. Works very, very well. And it doesn't take a lot of parts. The kid does this as well. Oh boy, this is something that's really going to interrupt your game here come this summer. Does everybody know what's coming starting July 1st? Rapid shutdown. Massachusetts is the first state to adopt the 2014 code. July 1st, both Colorado and Washington State. Oh, that's an interesting combination. What else do we have in common? Anyway, both of those states are, yeah, I was going to remember. Both of those states are adopting the 2014 code. Now, there's a difference between adopting and enforcing. Well, they're already starting to enforce it in Massachusetts. Why? Well, because we were doing a dealer conference back there a few weeks ago, and the head inspector dude from Massachusetts happened to see Ryan Stankovitz, who works for MidNite, doing a talk, and he was talking about this, and he had a demonstration. And the inspector says, all right, that's it. There's a product that exists that makes it so, yeah, the product exists, so, well, Washington State's going to demand rapid shutdown. Here's the problem. There is no standard for rapid shutdown. We have ETL quoting it right now. I'm not sure they're going to do a very good job because they were talking about testing the button 100,000 times. Now, granted, this button might actually get pushed once a year for 20 years. So I don't know what they're going to bid us to test it 100,000 times. But I believe CSA is going to be getting it to quote that too. This is going to be very important. It's expensive. It's complicated. And we don't have any choice. Oh, and MidNite Solar is one of the only companies in the world that have the rapid shutdown. It's standard product we already do. Here's kind of what it would look like. Combiners. Anybody here ever used a MidNite combiner? So a few of you, good. We make more combiners than anybody else in North America. Why? Well, because they're good combiners and they're inexpensive. Most of the grid tie stuff that you guys do have the combiner built into the inverter. Or you're doing in phases where you don't need a combiner unless it's an AC combiner. We do those as well. Inverter systems. Okay, I've got about 4 minutes left, so let's talk about inverters a little bit. We do a lot of pre-wired inverter systems. Here's an SMA system. That unit on the top is an autoformer because the SMA is only a 120 volt inverter. So that gives you the 240 volts either output for a grid tie or off grid, or it can be 240 volts coming in, stepping it down to 120 from a Sunny Boy or any other grid tie inverter. For some reason, German technology developed a 240 volt grid tie inverter and a 120 volt battery based inverter. Makes a lot of sense, huh? If I had time, I'd tell you why, because we know Outback was very instrumental in making that happen, by the way. Anyway, we sell quite a few of these. It's a very, very good inverter, and it's also very Germanish. But it's rock solid. It's quiet. It's probably the best inverter for regulation. on the market. We also do a lot of Schneider or Xantrex systems. You don't have to buy pre-wired systems from us. You can also buy the E-panels. We do lots and lots of E-panels. That's the box down below here. This happens to be something that Solar City is buying from us, installing in California. I know Solar City is not a good name up here, but it is from the context of we sell Solar City a whole lot of stuff that's installed in California. So that part's good. Anyway, the Xantrex XW is a pretty decent inverter. The reason Outback designed the Radian was to compete with the XW. And the Radian's a pretty good inverter too. Well, here's another new Schneider. This one's was designed to compete with the Magnum Energy inverters. This is built in India, but it's a pretty decent inverter. It's a little 2500 or 3500 watt inverter. This happens to be two of them. And we just got the E-panel ETL listed on that last week. Here's the Magnum inverter. This is by far the biggest bang for the buck. It is not the most sophisticated inverter, and it's not a grid tie inverter, but it's a 4400 watt inverter that retails for $2,700, and they sell lots of them. But like I said, it's not the most sophisticated inverter. Anybody who had ever lived off-grid with an Outback inverter would never accept this inverter, because every time the refrigerator turns on, the lights dim. It's really annoying. But if you've never lived off-grid before, you don't know any better. And it's cheaper. It saves you about $1,000. It's a 240 volt inverter as well. Here's an Outback inverter. We don't buy the Outback inverter any longer. Sorry, Brian, they got too hard to deal with. We do buy the SMAs and the Magnums and the Xantrex. But we do all the pre-wired, other than installing the inverter. We do the E-panels. And here's a combiner box for batteries here. And here's an Outback. This is basically what we started with about 8 years ago. E-panel for an Outback. End of slideshow. How about that? Any questions? Yes. Yes. Lithium ion's easy. All you're really doing is a bulk charge. The battery management system actually does the managing of the batteries. And if you don't have a battery management system, you will have a fire. So basically, any of the charge controllers can support lithium ion. Took us a long time to figure that out. Any other questions?
Why do you want it to talk?
Because we can.
Isn't that a waste, though? That's what we found out. Our early charge stations for the electric cars, they talked, and they just realized it was kind of a waste of the power.
Well, it doesn't waste any power to speak of.
You know, I mean the speakers wore out too, but the electronics. They said
it costs us $1.50 to be able to make it talk, and it's going to say things like, yeah, it's time to check the water in your batteries. It's time to equalize your batteries. It's going to do some very, very useful things that people just forget. Like, take me. I've got a golf cart that I've had for 10 years now, and I've gone through a set of batteries. Now, I know something about charging batteries. I've been doing it for my whole life, right? And even before 25 years of designing inverters, I was designing nuclear bomb launchers and aircraft power supplies that charge batteries. You know how many times I've checked the water in my golf cart? Twice. So, yes, it can be very useful to have it talk to you. And with the Whizbang Junior, we know a lot about your system. Any more questions?
You foresee any supply bottlenecks with the rapid shutdown?
Oh, I foresee lots of bottlenecks. We don't know how many we're going to need to build, and that's a big problem.
My question has to do with what's the real purpose of the rapid shutdown in the early date of July 1st, which is relatively soon for construction?
Firefighter safety. Why would they want to get on a burning building with 600 volts DC floating around? And firefighters have been taught to always treat solar panels like they're live, even in the middle of the night. So So yeah, that's true. So this is all about firefighter safety, and that's why the states are adopting it very, very quickly. Now, has anybody figured out what the writing is on the back of that casting? No? Close. Very close. It actually might be. If you look up on Google, alien abductions, 1959, Brazil, you'll find that that's supposed to be the writing on top of a door on an alien spaceship. Now, don't ask me why I put it on there. I just did. On the shutdown? Sure. So here's what the rapid shutdown actually requires. You have 10 seconds from the button push, which has to be on the ground. And boy, the rules are very, very vague. It doesn't even say whether the button has to be inside or outside. That will be up to the inspector. So you want to talk to the inspector. So you push a button, and it's supposed to bring the voltage of the whole PV system down to less than 30 volts in 10 seconds. Well, there's some problems with that. Take a grid tie inverter, a string inverter. Those capacitors on the input will stay charged for as much as 5 minutes, depending on how it was shut off. Well, we can actually deal with that too. We have the birdhouse that we call, the button. It's got 3 sources of power. Number one, it's got the PV array that powers it during the day from your combiner, let's say, or it just could be a shut-off box. It doesn't have to be a combiner at all. That sends 50 volts down to the birdhouse, and it keeps it alive during the day. At nighttime, it is powered by the grid, 120 or 240 volt input. But firefighters, when they come on a burning building at the middle of the night, one of the first things they do is they pull the meter. So it's the middle of the night, so the solar array is not powering this thing. And they've just pulled the meter, so the grid is not powering this thing. So what's going to happen when you push the button? It's got battery backup inside. That'll keep it going for a couple of days. So no matter what happens, it's going to turn off your shut-off switch, and we're coming out with shut-off switches now that'll do 2 MPPT outputs for some of the newer grid tie inverters, transformerless inverters. You have to actually have 4 switches because you have to switch off 2 pluses and 2 minuses for let's say the SMA TL series inverters. And by the way, competitors that use contactors on their rapid shutdown systems, they may never pass the UL standard once they write it, because once you push a button on a contactor, all you're doing is you're interrupting the power supply that keeps the contactors closed. Well, if you've worked with contactors much, you'll know that they don't always open up. They can weld themselves shut, especially with 600 volts DC on them. We have positive feedback on our birdhouse. It's hardwired. One of the poles of our switch is there just specifically so we know what position the switch is in. And we have a light that turns on that says that's on or off. And it talks to you and it tells you if it actually went off or not. Yeah, that's part of that talking thing. The rapid shutdown, gosh, there's many parts to it. The simplest would be just a shut-off switch up on the roof, turning off a grid tie string inverter. And it can have 2 contactors, it can have 4 contactors, or it can be our switch. To go further than that, if you have to shut off that grid tie inverter input, which doesn't want to come down to 30 volts in 10 seconds, you can put another switch right at the input of the grid tie inverter. Your inspector may require that. They're not stupid. They're going to know that, because they're going to be reading about this, they're going to know that that can stay charged for 5 minutes. But we do have a fix for that. It's adding a whole other switch. And these switches aren't cheap. I'm sorry. What happens if you have a battery-based AC coupled inverter in the house? When its job is to put out 240 volts when the power goes out. Well, we have a fix for that too. We have this thing called the battery disconnect module. And it's powered by the battery bank. And it will shut off the 250 amp breaker or the 175 amp breaker. We have lots of different breakers that are shunt trip. It'll shut off the battery-based system at the same time you push the button to shut off your grid tie inverter. Well, what happens if you have a generator? You know, those things are, some of them are designed to turn on automatically when the power goes out. Well, you throw another one of our switches on the generator, and it can shut that off too. The generator may start, but it won't produce any power beyond our box. It's very complicated. It's not cheap, but the alternative going forward for the 2017 code very well could be module level shutdown. And that's something that most people don't want. Yes? Solar Edge has done a very good job of it. Other people, of course, you have to buy the Solar Edge inverter. Well, let's say you want an SMA inverter or Fronius or something like that. You'd have to use Tigo type of products. Everybody familiar with what Tigos are? Okay, quite a few people. Anybody installed Tigos? Has anybody have to gone back and uninstalled Tigos? It's fairly common, by the way. Tigos have lots of problems. They actually cost you 1.5% power if there's no shading. They're great when you have shading. But if they don't have shading, they cost you power because they have transistors and semiconductors in series with every single solar panel. They are controlled wirelessly by Zigbee. Firefighters hate wireless emergency shutoff switches because they're deemed as unreliable. One more question? Microinverters solve the whole problem too. However, not everybody is a microinverter fan. Ask people that have had to reinstall a lot of end phases that are starting to die like flies. Then none of them, not a single one, will last that 25-year warranty. Yeah, we're working on microinverters too. That's years down the road, but they're not going to last as long as a string inverter. Thank you.
The perfect question to segue into our next presenter here. Let's give a warm welcome to Tim Faley, everybody, from Blue Frog.
How does this work? So right is forward. Okay. Hi everyone, I'm Tim Faley, and I'm so glad to have that segue. This is actually new news for me. My understanding was that the NEC had pulled that back out, and so this is obviously a change for us that it's being put back in, and so we're going to work on that. It's good news for a microinverter manufacturer to have this as a problem to deal with, but I'll get to that in a little bit. So we're running a little bit late. I had trouble keeping this to 30 minutes, so I'm going to bust through a few of these slides pretty quickly to try to be done in 20 minutes. This is just introductory. I'm Tim Faley. I originally started Blue Frog Solar as a made in Washington to make microinverters that were registered with the Department of Revenue as being made in Washington. Kelly Sampson and myself approached APS, which some engineers out of Silicon Valley that started producing and manufacturing offshore, had markets outside of the U.S., and we're looking for a way to introduce in the U.S. So we set up a plant here, and after a few years, we're able to work with APS to get started in the other 49 states. And we're very happy with how that's been going. We're now ranked #2 in shipments for microinverter suppliers, as a microinverter supplier. So that's been going. We're very happy with our progress there. I am not an engineer. I came to have a much more general discussion about the benefits of microinverters because we manufacture them. Obviously, everybody here is very familiar with a lot of this, so that makes my job easier of bumping through this. These are the two topics I want to talk about tonight, benefits of microinverters, and then a little bit about where the industry is headed. And I mean in general as far as solar and in the world, and where do we think markets are going to be in the next few years. This is I put this up because most installers that we talk to around the country are, this is always in the back of their minds. You know, they're more expensive. They do a good job dealing with doing what they're supposed to do. String inverters are cheaper. They're easier to install. So this is kind of the mindset. And there isn't anything about this that I'm going to exactly turn on its head, but the truth is much more complex and much more detailed, and it's in the nuances that I think the market is changing. Because what we're seeing here is, considering that 10 years ago there were no microinverters, this is the market we're seeing today. There are tremendous inroads being made in installations, and so the whole market, including DC optimizers, is variously referred to as MLPEs, module level power electronics. In this case, we're not going to really deal with DC optimizers tonight, but microinverters are definitely making inroads. Benefits of microinverters, I'm going to try to bust through a lot of this here and just deal with a few of these, but these are the major advantages of dealing with microinverters. The design simplicity and flexibility are really two sides of the same coin, but they do deal with different areas. Designing string inverter systems requires a certain level of knowledge, ability to deal with all of the factors. There are temperature variations on any roof. There can be irradiance differences. You have to calculate you're trying to stop the bottlenecks, obviously. Flexibility is more redesign on the ground, if you will. You run into different shading issues on the roof once you're there. If you have string lengths that have to be slightly different, so you can have different loads that you need to balance. It's easier to expand later on. Speaking of flexibility, so this is a slide. You wouldn't believe how often we need to explain this. I get questions all the time. If you have an inverter, and I'm assuming a certain level of knowledge, we produce our main model is the YC500. It's a dual MPPT unit, handles 2 modules, both fully separate. You could unplug one and the other would still be maximizing. 250 watts out per side, 500 watts total. But the question I get all the time is 250 watts. Well, what if I have a 280 watt module? And you know, that's just so to be clear for anybody listening that's not clear on that concept, it's 280 watts DC at roughly 40 volts, 45 volts. When it gets converted to 240 volts out, you're dealing with much less than 250 watts AC. So 250 watts, and it's the same as the Enphase 250. It's a pretty powerful setup. You can handle a 300 watt module. This is the clipping. So this is a picture that we're looking at now that deals with the clipping that one could deal with if you did generate too much power. The trade-off is that orange at the top is the power that you would lose with having a more powerful module. What you gain, though, in having that greater production is you're generating more earlier in the day and continuing later in the day. So I just wanted to throw that in. Hopefully that'll answer some questions. String inverters have other balance of system costs that aren't always addressed. Everybody here has their own opinions about that. I'm not going to get into that tonight. The primary advantage of microinverters is what's called mismatch mitigation. There are a lot of areas that this covers, but in effect it's the bottleneck that's created when one module is creating less current in the string. There are enough types of mismatch that really we recommend 2 categories. There's hard and soft. The hard is specific to the location, and it will vary from location to location, and we always think of shade. It can also be something in the angle of the roof a little bit that can have irradiance differences, module to module. Soft mismatch is everything else that you can't control when you're doing the installation. It's what comes back later. So we'll get to that in a sec. So hard mismatch, shaded arrays, 6.9% is almost an arbitrary number. It's an average over countless numbers of installations. Somebody spent a lot of time putting that number together, but it's obviously there's some number that averages out. I have a graph coming up for that. There's dust, slight angle differences, again, irradiance. This is an example, as much as anything to pull from this, is how much it can make a difference in winter months to summer months. I don't like to read too much into anything that can be exactly wrong because it changes from roof to roof. And even areas that have just one little bit of shading versus a large tree, it changes from year to year in angle of the sun. But this is the one that most people think of when they think about mismatching is shading. But there are so many others. In soft mismatch, you're dealing with the binning, which is the different modules. If you're buying 30 modules for a roof, maybe one of those is producing slightly less, even 1% less, and it can make a big difference over time. That's going to reduce the entire string. Thermal mismatch, I'll give a graph for that in a sec. And then the long-term degradation of the module that you can't predict in advance. So here's an example of thermal mismatch. So when you're putting a large surface area of modules on the roof, the ones on the edge are going to be a little cooler. The ones in the center, less air circulation. It's going to be uneven. So you've matched your string. You've done everything you can to have everything set, and now the temperature kicks in, and it's less efficient in the middle. It's hard to plan for that. So microinverters take care of that. Long-term breakdown. Most of them degrade, and the industry standard is you're expecting 0.5% a year. If you have one that's maybe 2%, that's going to throw your string off. Monitoring data. Boy, there are advantages. It helps sales to consumers, but I know installers have a hard time with that. We have a hard time with that. I'll talk a little bit more about that later. It's a lot of work to get that data together, and it's kind of a double-edged sword. So it's something that we all work with, and I think there are opportunities for that in the future. And this gets to the safety. This gets to this is a problem that string inverters have. Microinverters shut off. They're designed to shut off as soon as the power stops. You're still generating DC current during the day coming from just the module, but it's so little as to be inconsequential. So this was before 20 minutes ago my understanding of how the world would be. So we had until 2017 to work this out. So this is new news. That's very interesting, and so we're going to have to do some work to figure this out. Failure rates. Microinverters, string inverters generally fail at about the same rate. It's just that when a string inverter goes, the whole system goes. If there are 30 microinverters on a roof, they're 30 times more likely that you'll have one fail than in a string inverter then. And so it ends up happening apparently more often. Consumers are, they suffer less when they have a failed microinverter. The installers suffer more. So it's an ongoing issue. And it's depending on what side you're on, trying to figure that out. And that's something we're working on as hard as we can. APS has a failure rate of roughly 0.5% around the world. In Washington, our first generation YC200s was much higher. Our local reputation, we're still trying to recover from that. The YC500 is very close to, it's under 1%. We're about 0.7 now for Washington State. But that's something that we're continuing to work on. Monitoring, to me, this is an interesting issue because it's a terrific selling point when you're working with consumers. And they love to see that. They love the idea that they're going to be able to look at the computer screen and follow their system. It takes extra work. It takes extra knowledge to be able to put this thing together. You've got to have a guy inside setting this up. It takes extra work on the part of the installers on the roof. They have to map each module. And we find that the biggest problems come when people don't. It's the education problem that Enphase has had forever. And if somebody has been installing string modules and they think, so what else is to know? And they go put the whole thing together and then they realize they needed to record the location of every serial number in that array, and then they had to put it down on a piece of paper and then get it into the computer accurately, because otherwise what use is this map that I see on the TV screen if I don't know where everything is? So to me, one of the future technology issues is going to be solving this in a way that takes all the labor and the guesswork out of mapping the system after it gets on the roof. That's something we're working on continually. The costs also extend to us. It extends to any company that offers this kind of a service. We don't charge for the software or the monitoring of this. We do charge for the ECU that monitors this unit or monitors the array. And then the continued cost of that system is factored in. So it does create extra work for everybody. And it behooves us all to try to lower the cost of setting that up. So a little bit, just a little bit of a discussion of where we're going from here. The industry is going to enter a new phase coming up. I think the next 3 years are going to be critical. Price competition is going to be what's going to drive all of these installations. We're all looking for ways to get these systems to be more competitive. When we started installing a few years ago using the Washington incentives, we were looking at 8 or 9 year paybacks. As we get down to the newer generations of equipment going in, now we're looking at 4 or 5 year paybacks. So we're still able to stay in range with this 2020 goal that we've had. Technology advances, and that's something we can talk about in the market cycle. So the competition that's been going on, looks like we lost a word there. Companies, existing inverter companies. Yeah, okay. Anyway, we're seeing a lot of shakeout from different companies. One of the companies that we viewed as a competitor, Nexus, has been having a lot of trouble. I don't want to go into it here, but we're going to start seeing others drop out, and it's going to consolidate. Also, others will be purchased. I mean, nobody's outside of that game. I mean, Enphase may be one that will be picked up in a couple of years. That's just the game that's being played. So it is about the price. It's all about the levelized cost of energy among the different inverter manufacturers, trying not to be commoditized like modules are. So getting into product differentiation, it's about marketing, showing bankability. Enphase appears to be very bankable, but as their sales go up, so do their losses. They're not able to, so that's an issue. That was a Nexus's problem, as they were discounting everything too cheaply and losing money but making it up in volume. we like to think that we're doing pretty well on that score, and we hope to really show bankability pretty soon. Reliability is an issue for us locally that's important in the room. I think I talked about that a little bit, but that will be critical in terms of differentiation in the future. And the software and service, obviously, I think that's where the future of it's going to go. For the technology advances, we're now, I put AC modules in here because that comes up over and over in other sectors. I don't think that's going to be that critical because, or that important. I think it's kind of a gimmick because it's shown as being the easy way to put a system in, but what you have is two components going together, both of which are developing at different rates. And it's a big risk for anybody to take on a large consignment of a product that now has two parts to it that have two different technologies that are improving. I've mentioned this a few times, improving the software to capture the UIDs of the modules, I think is critical, and whatever company puts that together and controls that technology will really take off for microinverters. We recognize that, certainly. I think one of the things that's going to change the market for microinverters is the upcoming three-phase inverters that are coming out. That won't make such a big difference residentially in the residential market, but commercially, which is where everybody's shooting, that's going to change. That's going to change so many parts of the game. APS is working on one right now. We have one. I have one in the back room if anyone wants to see it. Three-phase microinverter can handle 480. That's part of where the system is going, where the new designs are pushing. I think that'll be very interesting to watch. We're trying to have that rated for Washington made as well. We'll see. And then just nationally, it's taken us however many years to get to 4.75 gigawatts as of 2013. That's going to double in 3 years. So that's and Washington State has every reason to expect to be part of that. That's think about that. Think about that number. That's huge. But I do think that beginning a little bit after that, we're going to start losing incentive systems, and as the others talked about, the utilities are starting to push back. This is the last slide. If you have any questions, I do just want to bring up an additional point about utilities. I think that's going to be where the next that's where the next major disruption of our technologies and economies are going to be. It's a chance for the next, I don't even know how to have a huge conversation equivalent to superhighways or whatever. It's accepted within the utility industry that 10 to 20 years from now, it's going to be a decentralized community. It's not going to be centralized. That's going to be fought. I mean, think of there's even a Dow Jones, I mean, it's such a huge world of people whose retirement incomes are based on these systems that are thought to be so safe as investments, and yet these are the ones that are now the most at risk. It's hard to even imagine how that's going to change a lot of people's lives. And so the challenge, all of those companies are reacting to support their shareholders that have completely different interests in their portfolio than they do in trying to heat their home or get electricity for their roof. So this is going to be very interesting to watch how it plays out, and smart grid systems are part of where it's at. We're only in the first 2 or 3 generations of, I mean, I think of, compared to, this is like being in about early 1980s for microcomputers, and now we have these guys that can do stuff we couldn't even imagine, but that's where we're going to have to be in another 15 years to make this work. Anyway, so questions?
You said you had a failure rate of 0.5% to 2%. Is that per year? Or what is that the life of the inverter?
That's the life of what's installed so far. We're about 2 years out on those units in Australia, China, California, Hawaii, parts of Europe.
Can you say something about heat issues with microinverters?
I'm sorry?
Heat, temperature?
Yeah. Well, efficiency, we're running around 94, 95% efficiency. Are you talking about as far as heat, summer heat, roof heat? Yeah, well, they're rated at 65 degrees centigrade, just it's standard UL, 85 ambient. I mean 85 internal and 65 ambient. We're using them in Arizona where rooftop temperatures are easily in excess of 120 to 140 degrees. We haven't had troubles. We use them in Hawaii and in the Outback in Australia. Have not had, I mean, since we're able to monitor them, we can watch the temperature, and it's extremely unlikely that they even get above. I mean, 65 C is roughly, I think, 165 Fahrenheit, and we haven't seen them approach that temperature in any of the conditions they've been in. Well, it's obviously more efficient in lower areas. Actually, Washington State, an argument that I make with people that somebody commented that it's lower here than anywhere else, I mean, than other places. And lower temperatures definitely make higher efficiencies. Well, right. I mean, but it shines all the time in Arizona, and we actually pick up quite a bit more per square foot with our temperatures.
So not sure if you can share this, but if you're willing, how much of your business is outside of Washington versus in Washington? And similar question as I asked Outback, in what ways is the company as a whole kind of affected by the production incentive program here?
I would say that APS is not affected at all by the production incentive program. I mean, it's Blue Frog Solar is affected quite a bit. Let's see, you were asking as a percentage. I would say that Blue Frog sales are in Washington State are probably 5% of APS sales, and as a percentage, that's falling. We ship container loads. We usually, as APS, only deal with pelletized consignments, or I mean, we send them by the container load to distributors. Here we work, if you need 4, we send them. If you need 15, 20, I mean, it's our model here is more as a distributor, even though because we started here and expanded through APS, it's not exactly a distributorship relationship, but it's as if we were a distributor.
I'd just like to make a comment. You talked briefly about the 3-phase APS.
Yes.
One of your customers, 10K Solar. We just got a 3-phase combiner listed for that inverter, so they're planning on doing big things with it. It is very unique.
It's an interesting product. It'll be interesting to see how it develops. It does 900 watts AC out, It works with 3 or 4 modules, each unit. Because it's 3-phase, it suddenly opens up different possibilities that you're used to, that you hadn't thought of. For instance, a typical string length using 12-gauge wire might be 16 modules, and you could bump up circuit breaker from 20 to 25 amps and maybe get to 20 modules. A 3-phase, we're using 14-gauge wire, and we can fit 13 of these that can hold 52 modules in a string because it's 3-phase. So it's a pretty interesting development for larger installations. It's a product that is going to work in the roughly 25 cents a watt range. The top end would be 30 cents a watt for low volume installations.
So what's the voltages on those 3-phase?
480,
480,
208. It'll work in either range.
It works in like 380. Are you paying?
Yes. It's just not so common here. Same inverter. It gets programmed at the factory. Okay. Okay, you bring up a very obviously any piece of electronics, who knows? The components inside it are well tested. I mean, there's nothing. A piece of electronics is composed of lots of smaller components that have all been used in other areas. Any type of manufacturing. This is outside of the subject, but I know that Enphase is changing to a 10-year warranty very soon. APS is working on moving to a 10-year warranty with the ability to sell the 15-year warranty. And this move is being pushed primarily by Enphase's investors, who feel that this is basically an unfunded liability. So what APS is looking at, and so they're going to just a straight 10-year run, and that hasn't been publicly announced yet, but it will be pretty soon. Our view is that there is a market for 25 years. It doesn't mean, I mean, we think the expected life is 25 years. But to make it then an unfunded liability, or at least acknowledge it and keep track of who's willing to pay for what. So we made a decision at Blue Frog that when that time comes, which is pretty soon, that we move to a 10-year warranty. I mean, I say when. Some people would say we already have, but it's not effective yet. Blue Frog is basically going to be, we're spending the extra money to make it be a 25-year warranty until we can get all of this worked out. So to me, it wasn't an issue that I was bringing up, because you'll hear about a move to a 10-year warranty, but it won't affect sales. It won't affect products sold in Washington State. This is, for us then, this is money that we set aside in the event other units need to be replaced. And I should mention that APS is the one standing by the warranty. And this is, you know, they're very, very well capitalized. It's just that they're a private company, so it's just it's not financials that you can talk about.
That 25-year warranty on modules is kind of weird. I mean, that has to do with their output. It's not supposed to come down below 80% or whatever it is of its original output. But at 15 years, for instance, if the module goes to 0, if it's broke, they don't cover that.
Yeah, the question was about 25 years and how that's measured. And you're right, that's a good point. And that was pushed originally because solar modules are 25 years. Enphase came along and tried to match that, only they can't quite do it the same way. So there is a disconnect. It's much more complicated electronics. You've got it, potted up in this box, and it's water. If it's done right, it's waterproof. It should be static. It should take practically an unlimited number of times of cycling, but you can't prove it until you go 25 years. So what you do instead is you set a fund aside and say, okay, if one breaks, we're going to replace it. And you just, well, that's the, and they were all considered very bankable. So yeah. Anything else?
Will you be offering an extended warranty?
Yes, so it's APS will be offering an extended warranty, and the basic nature of it is that it will be, this is APS, not Blue Frog. What I'm saying is Blue Frog is going to be doing the work to bring it up to the 25-year level. The 10-year warranty, so the unit gets sold as a 10-year warranted product. If somebody chooses, if an installer has a consumer that wishes to go to add 15 more years to the warranty, the consumer would go online to a website that's being set up specifically for that. They would type in the serial numbers of the units that they are purchasing the warranty for, use their credit card. This would be outside of the transaction. So we would keep a database of all of those. But if in 5 years somebody calls, or 5 years it doesn't matter, but in 11 years if somebody calls, we would look up the number. If their number shows up, they're good. Otherwise, we have an inverter we'd like to sell them. So. Oh yes, yeah. It's not by owner. It's by the. It's actually. It's not transferable from the address. Let's put it that way. It's registered by address. How long has APS been around? First started in 2009, and it was originally started by a couple of Silicon Valley engineers who specialized in cell phone technology and working with field programmable gate array chips. How are we doing on time? Okay. All right. Thank you.
All right, let's go ahead and give everybody a round of applause again. Thank you.
Muted. Unmuted.
All right, so this concludes our meeting. Before we go, whoever wants to again meet up just up the street, please join us. You're all welcome to. Also, most of you should have gotten an email from Patrick this week asking about, I guess last week, asking about meeting locations. This is hopefully our last time here at the zoo. We are looking for a permanent location. That means we have 2 months from today, give or take a couple days, to figure out that location, and we're hoping to get everyone's feedback. So if you haven't already done the survey, we're going to send out another email with the reminder in it. We'd love to have your feedback. But thanks again for coming tonight, and we'll see you next time.